It was the first day in my new assignment for a car manufacturer, and hundreds of people were streaming through the exhibition hall during the day. I was there to answer questions about what the Agile transformation would mean for them in the development of the physical car, the chassis, the interior, the exterior, basically everything you can think of that you can see on a car. Agile doesn't make sense for hardware development. This comment came up many times during the day. Let's explore this statement by breaking it down into 3 common preconceptions about agility in a hardware development context based on some of my learnings in the automotive industry. My name is Christian Fredriksson. I am a freelancing consultant with my own company and also associated trainer and consultant with We Are Moment. Make sure your seatbelts are fastened because this will be a fast ride. Let's dive right into the preconception number 1. We can't create cross-functional teams. And so many specialized skills and so many people and suppliers are needed just to create, for instance, a braking system. How are we supposed to be able to deliver any kind of value with a small Scrum team of 3 to 7 people that can design, build, and test? And what is even a team in this context when there are so many dimensions we need to balance and optimize for? Should we split by hardware or software, car program, geometry? Seems like we always tend to end up with a very large team. Let's have a look at what 2 Japanese researchers showed us about cross-functional product development teams that served as an important inspiration when Scrum was created. Scrum even got its name from this article in Harvard Business Review from 1986. Cross-functional and self-organizing teams that Takeuchi and Nonaka had studied were developing copying machines, cameras, and cars, very physical things. And in terms of size, these cross-functional teams were quite large, more like 100, 150 people. So they showed much more resemblances with an agile release train. So back to our car manufacturer, it made much more sense for them to think about cross-functionality and value delivery from the perspective of a team of self-organizing teams. 120 people developing, for instance, the braking system, where teams then could be split, as in this example, with dedicated hardware teams, software teams, and mechatronics teams in those cases where hardware, firmware, and software were very tightly coupled. A team could then have competences such as developers, attribute leaders, and experts in doing simulations and testing, as well as the product owner and Scrum Master roles we are already quite familiar with. There were also other roles on the train or teams of teams level serving the teams, such as quality, manufacturing, engineering, and procurement, as you can see here. But even though we could create cross-functionality on the team of teams level from one perspective, in this case, the braking system, and to be able to decelerate the car, there were still so many dependencies towards other parts of the development organization to also optimize and balance for other dimensions, like geometry. Everything needs to fit together in the car in the end. If there, for instance, would be a need to make room for larger wheels, it could require the collaboration between many teams working in diverse areas across the development organization. And in order to handle this, we introduced some more self-organization. Prior to the quarterly PI planning events, the mechanical integration team did an experiment where they set up something called a gallery event. It was like an open house where mechanical integration had done preparations about geometrical areas that needed extra attention to make everything fit together. And they then invited all teams to visit the gallery to find their dependencies and then facilitated the collaboration between those teams. This made the teams better prepared for PI planning. Mechanical integration were also helping out during PI planning itself to facilitate the collaboration needed to resolve issues related to dependencies that was discovered during the planning. So we had found a pretty good way to organize and self-organize hardware development teams on a large scale, but that led us to the next common preconception. It doesn't work to delegate decisions to the teams. We need to make decisions centrally. Actually, the organization moved quite far in empowering the teams to make their own decisions. And even though such a change is very much about organizational culture, there is also another aspect to it. In an environment when so many people are building an integrated product like a car, just delegating decision-making to the teams will lead to quite bad decisions if we don't also enable the teams to understand how the decisions they make impacts others and contributes to a balanced product and a great customer experience in the end. So if we are working with the wheels and tires, how can we make sure that we optimize for the whole and not only the wheel? There are a lot of different attributes to balance and not only make a good wheel, but even more on the complete car level. The decisions made in a team developing wheels and tires can have an impact on not only things like cost and time to market, but will of course be very important for success of the complete product, but also other complete vehicle attributes like weight and energy efficiency. So if I'm a product owner for this team, how do I know how to prioritize a possible weight saving, for instance, if it will at the same time have a negative impact on time to market and passenger comfort? By working to make the value of these trade-offs visible and comparable, how much will reduced road noise be worth to the customer? And what is the cost of delay, for instance, to consider if we have a timeline implication on this as well? The team could easier understand the impact of their work, which enable better local decisions and shorter feedback loops. And this brings us to the third and final preconception. Feedback loops in hardware are too expensive, I was told. So we better get it right in the first place. Yes, feedback loops are too expensive if we do them late. In this case, this is a situation that also anyone that has experienced failed traditional waterfall projects in software development will be quite familiar with. Late surprises and firefighting task forces. The thing with hardware development is that the cost associated with doing late changes when we have passed the line that you can see here are usually extremely high. We have a factory that is waiting to start production. We have hundreds of suppliers involved. We might even need to make changes to very expensive tools and have impact on complex logistics chains, have to fly things over the world, etc., etc. Still, doing these late feedback loops with all the firefighting is quite common in the automotive industry. Compared to complete digital products and services where we can build and ship things in seconds with almost zero cost, in the hardware world, we still need to live with the constraints associated with building physical things. So what if we could instead avoid doing all these costly feedback loops late in the process by doing more of them earlier when it's much cheaper? As with software development, we are still in a knowledge creation process here, and we want to avoid having bad surprises late in the process by generating as much learning as possible early, before the line in this case. And that's where we need those feedback loops. It's also before the line we can do a lot of the work virtually and digitally. But in the hardware development, even when the feedback loops are done virtually, with different simulations, etc., they are still usually much more time-consuming than in the software world, not least when considering lead times when working with suppliers, as the other Christian talked about earlier. So there is a limitation in how many feedback loops that can be done in the time we have available, and what we can do when that doesn't take us far enough to close the knowledge gap and avoid later problems. Let's do them in parallel instead. So for instance, if we're developing a wheel suspension, we could do several different concepts in parallel to generate as much learning as possible. This will give us important knowledge about balancing and trade-offs that we can then use as we converge into one concept that we then start iterating from. So after we have explored these three preconceptions, what can we learn about agility and hardware development? It turned out that Agile actually does quite a lot of sense for hardware development. It can help solve some problems that can have very bad consequences and be extremely costly when developing things like cars. But we also need to understand agility in the hardware context, not only looking into methods and practices from a software development perspective, but also understanding the underlying thinking and principles. And we don't need to become software developers first to understand this. We could actually learn directly from where it all began, within the development of physical products and also cars, such as the work by these thought leaders that you see the books from here. Understanding the underlying thinking and practices for agility can actually help it make much more sense for software development as well. And no matter if we are developing software or hardware, to build great products, we need great teams that have the ability to learn and adapt quickly. Thank you so much for listening.